So, good evening to everyone. Welcome to the weekly discussion session for the NPTEL course Physics of Nanoscale Devices. This is discussion session week number 11, where we shall be covering the contents of the final week of the course. So, before we go on with our session, I'd like to ask our attendee if he has any questions or queries from the previous week's contents.
Yes, sir.
Yeah,
Sir,
please
I
go
want
ahead.
to ask the inversion layer which is mentioned,
Yes,
is that the
yes,
conducting channel of the device?
yes, it is. So,
Okay, sir.
uh, rather, I would say that the inversion layer contains the conducting. So, let me just like answer your question in a bit more detail. Just one second. So,
Sir, please prevent the
yeah,
share.
I'm opening the files now. Like
Okay,
I
sir.
had
Okay.
only the stuff open for this week. I had to go and open the last week's files. Yeah, I'll share
Yes,
the
sir.
screen right now. Um, so, screen. So, yes. So, can you see this?
Yes, sir.
Yeah. So, this is kind of what we are using to, like, these relations are what we are using to understand the behavior of our, like, the channel in a MOSFET in the three terminal device. So, first and foremost, the things that we find out first is the width of the depletion layer. So this comes from the applied potential and the permittivity and the doping concentration. So this defines the region in which inversion is going to occur. So we have WD, that is first. And it is also assumed, like according to this graph, we know that ES has some non-zero value at the interface and essentially the oxide semiconductor interface. And we also assume that by the time we come to the edge of the depletion layer, we are at zero electric field. So directly from that we can use the relation that the potential difference is integral EDS. So performing this integral will essentially give us the area under the triangle. So from this depletion layer width that we have calculated and the value of the electric field at the surface, which we can derive using, uh, how can we derive that? Oh yeah, we don't have to, like, essentially this will be the known quantity. Psi s will be the known quantity because we apply a gate voltage here and there are going to be some capacitances. So we uh, account for the effects of the capacitances and find out the surface potential. So now using the surface potential and the depletion layer region width, we can find out the electric field at the surface. So ultimately from here, we use this relationship to get the inversion layer thickness. It's kBT by Q divided by the average electric field, which you can assume to be the surface electric field for all intents and purposes. And from that, like if you like divide, this has the units of potential kBT upon Q. So dividing that by an electric field will give us the dimensions of distance. So that gives us an how do I put it? Like it is not the exact distance at which the inversion layer begins or ends, but this is kind of an estimate because we know that the electrons that are moving in our material are kind of, like the mobile charge carriers are present because this conduction band has kind of dipped below the Fermi level. So in many ways, the energy of the electrons present here is actually the thermal energy. So that is why we use the thermal potential here. So that divided by the electric field will give us an estimate. So that is how we arrive at the inversion layer thickness, and that is the actual thickness of the channel within the depletion layer. So the depletion layer usually comes out to be something like 30 or 40 nanometers. Yeah, if you can see the videos for last week, which should be up now, um, you'll see that the depletion layer thickness comes out to be around 30 nanometers. But after that, if we make some calculations, like with some approximate values for size and whatnot, we'll find that the inversion layer thickness is roughly to the order of 7 or 8 nanometers. So even in a bulk MOSFET, like yeah, all the analysis that has been done here, this is for essentially a bulk device. Like this is not a ballistic MOSFET. So for a bulk MOSFET also, the channel for all intents and purposes is actually a nanoscale channel because the mobile electrons are all confined in a region of thickness of only a few nanometers. Okay, so that is how we arrive at the inversion thickness, and that is the actual channel through which conduction takes place. And when we talk about pinch off and all these things, when we consider device saturation, we are talking about the pinch off of this inversion layer. I hope that answers your question.
Yes, sir.
All right, any more queries?
No, sir, not regarding this. Just I want to
Okay.
ask, is this the last session?
Uh, Actually, yeah, let me just minimize the thing and stop presenting for a second. Yeah, so the truth is, I do not know. Like, we are supposed to do 12 sessions, and this is week 11. So, there is supposed to be a session 12, but yeah, I have written to the folks at NPTEL. When they get back to us, and of course, if there is a session, the course page will make the announcement. So, I guess you guys can simply check that out. And if it is there, of course, I will be here. Uh, so
Okay, sir.
that is the thing about next week's session. I mean, you guys would also know by now that your exam is on the 30th of April.
Yes, sir.
Yeah, so technically speaking, like the next session will still be 1 week before your exams. And if there is a session, then that session will be dedicated entirely to problem solving, where I shall, like, from beginning to end, I shall just solve problems. Even if a session is not there, I'll ask the NPTEL people if I can record a video on my own and upload it on that day itself, so that you guys can look at it before going for your exam.
Yes, sir.
Like
Actually, I was asking because then I will prepare this week from, means I will revise all the course and I will prepare some doubt questions that
oh
I
yeah,
can
yeah,
ask
by all
next week.
means. See, even if you even if the session is not there, please post your questions on the forums because I also look at your forums.
Yes, sir.
Okay, so even if we are not present at this meeting, post your questions and I shall answer them from there.
Yes, sir.
And in all likelihood, I think there will be a session, but well, let us see. Let us see how it plays out. Okay.
Okay, sir.
All right. So let us begin the session for this week. Again, like last week, we'll not be writing too much today because there isn't much new stuff to be covered. So essentially, I shall be using the slides of the lectures themselves. I shall be making the annotations on them, and I shall share these slides with you. Like this has also been the case for last week. If you check the drive, you'll see that I've uploaded, essentially re-uploaded the lecture slides with my own annotations from last week's session. We shall follow
Yes,
the
sir.
same format. Uh, yeah, all right. So let me share the screen again and let us begin with this week's session. Um, no, no. Yes. Yeah. So can you see the slides?
Yes, sir.
Good. All right. So I hope by now you are familiar with the notion of strain engineering and the idea of leveraging quantum confinement in order to produce essentially enhance the mobility of electrons in a semiconductor. So a device that leverages quantum confinement greatly to boost its properties is the double gate silicon on insulator MOSFET. As discussed in the previous weeks, alongside of other benefits, this configuration also increases the shielding capabilities of this device. Therefore, effects such as DIBL are mitigated to a very great extent in these devices. So first, yeah, I think I will make a remark to that effect itself. Yes. So double gate. Oh, sorry. So let me just say that. Yeah. So if I have a double gate, then we this implies there is better screening. So this is something that I mean you do well to remember even in general. And better screening implies impact of VDS is reduced. So yeah, just 1 second. Oh, wow, okay. I have another attendee. Um, yeah, welcome to the session. So yeah, so in this case, like essentially DIBL will be low. All right. So and the last topic that was covered in last week's lectures are continuing with yes is the idea of strain engineering. So the notion is that even in like the idea of strain can be seen here itself. So when we have an insulator silicon interface, essentially what we have is like we have an SiO2 and SI interface. So obviously the lattice constants for both of these material are not the same. So when we have an interface that is built over here, there is going to be some strain that is developed at this interface because if I want to create a good interface, the lattice matching needs to take place. So due to the fact that the lattices are matched, whichever like there will be a strain on both the materials. In addition to this, we can also have certain geometric effects, like we can have like a gate envelope. Essentially, we can have a semiconductor channel. Like this is the what to say, like the view from the drain to the source. So the gate is above here, and we can have a gate that is deposited on top of the channel. So this gate, because of the way it is deposited, can either apply a strain in this direction, or we can have a strain that goes in the opposite direction also. So we can have a compressive strain or an expansive strain. So these strains are usually applied in one direction. That implies that the lattice parameters in one direction are changed. Now, in the case of silicon, we previously knew that the x, y, and z directions are kind of degenerate, which is why the isoenergy surfaces for the silicon band diagram are given in terms of 6 ellipsoids. Now, of course, the band diagrams and all other energy levels are given are essentially a function of the periodic potential, which in turn depends on the lattice constant. So if the lattice constant changes, of course, these energy distributions are going to change. So what we will essentially see here is we will have four, like there will be one direction along which there is a strain. So let us say that direction is the x-axis. So the red lobes shown here are the strained lobes, like the energy isoenergy surface here will be slightly distorted, and the blue and the violet regions are the unstrained regions. So because of this, what essentially happens is the energy levels, like right now we are focusing on like we are also assuming that this is a confined silicon sample, in that the energy levels are kind of discretized. So that confinement essentially occurs in these channels due to like either one of these effects. So this is when the electrons are confined by an externally applied electric field. This is the case when we have the formation of inversion layers and so on in MOSFETs. Otherwise, we can have like proper geometric confinement, as is the case with these double gate MOSFETs, where the what to say, like the layer of silicon is actually extremely thin. So silicon on insulator devices are also sometimes referred to as ETSOI, where ET stands for extremely thin. And extremely thin implies that there is quantum confinement, and quantum confinement implies that we have discrete energy levels. So those are the levels that are shown here. However, because of strain, what will happen is all these six energy levels do not behave identically, because the lattice parameters are changing in one direction. So because of that, we shall have two different sets of discrete energy levels. A rough idea, the motivation can be understood in terms of the like, since we are talking about one dimensional confinement, we can think about the particle in a 1D well. So for a 1D quantum well, we know that the energy is given by n squared pi squared h squared upon um, oh no, h bar squared upon 2n star L squared. So as we reduce the lattice constant, the energy difference will actually increase. So that is essentially what we have assumed in this diagram. What is happening is, for the red bar, we are assuming that there is a kind of a compressive strain, which implies the L is reduced. Since the L is reduced, these energy levels kind of jump up. They become higher, and the difference between them also becomes larger. So we have the blue ladder of energy, which corresponds to the unstrained energy surfaces, or rather the unstrained bands, and the red levels correspond to the strained bands. So these are essentially called the subband ladders. So as a convention, the unstrained bands are the unprimed ladder, and the it's the other way around. I'm sorry. So the unstrained levels are the primed ladder, and the strained levels correspond to the unprimed ladder. So there are two of those, and four of the primed ladder. So what this essentially does, because of these formation of subbands, essentially the effective mass will also change, because the effective mass is given by the curvature, or the second derivative of the ek diagram. And this, the isoenergy surfaces are an ek relation, in like, not in a way, they're literally the ek relations. So the curvature of this surface will determine what the effective mass is. Since due to strain, two of these have changed in their curvature, for two of these subbands, essentially what will happen is the effective mass changes. So because of that, we shall have a change in the net effective mass. And if we remember the previous analysis for calculation of electron mobility and so on and so forth, we will find that the presence of a second, like essentially the expression for the total effective mass is given by the harmonic mean. So the okay, I should put that in the subscript. Sorry, superscript. So the effect, like the total effective mass, is given by 1 upon. So this is the longitudinal effective mass, and this is the transverse effective mass. Like longitudinal and transverse are referred to with respect to the notion of charge conduction. So if you remember from our MOSFET electrostatics analysis, the x-axis was along the drain source direction. So this is ML, and we have four lobes, that is the y and z directions, which are perpendicular to the electron conduction direction. So they are the transverse lobes. So the total effective mass will be given by this relation, that is 2 upon m transpose plus 4 upon m longitudinal. So, and as you can see here, m transpose is much smaller than m longitudinal. Like m longitudinal is a very large value. So because of that, what essentially happens is the strain here increases the curvature so much that the effective mass comes down. So this quantity becomes very large. Not very large, like compared to this quantity becomes larger. As you can see here, like this is around 8 times ml. So you can see that this reciprocal quantity will become larger. And because of that, 1 over m star total will become larger, which implies the actual effective mass will come down, because I mean we are taking the reciprocal of this whole expression. So the introduction of strain of this kind in this material has reduced the effective mass of our electron, the combined effective mass of our electron, and due to that low electron effective mass, the mobility of the electrons also increases. So ultimately, when we are talking about quantum confinement or strain engineering, the basic idea is to change the internal energy configuration, energy level configuration for our channel, and through that we will achieve some kind of mobility enhancement. There are also other benefits for this. So essentially what happens here is, now because of the strain, there will be, like, so now we are moving on to the same situation. Oh, sorry, that diagram is over here itself. So now we have the same situation here. Yeah, so for the, now we are considering a case where there is a tensile strain. Essentially the material is being stretched perpendicular to the direction of conduction. So in this case, like for the purposes of symmetry, we are replacing the x-axis with the z-axis. So we have the strained bands here and the unstrained bands here. Or rather, wait, this is a biaxial strain. Oh, sorry. That implies, yes, the strain is in the xy plane. I'm sorry, my mistake. The z direction is the unstrained direction because there is biaxial tension here. So what we have are now two separate energy levels, and usually the lowest energy level of the strained band levels. I mean, no, I shouldn't say call them band levels. How? What shall I call them? So these are the discrete energy levels in the confined channel. So yeah, we can call them ladders. So the strained ladders will have obviously a different spacing compared to the unstrained ladders. So the first thing that will happen is, now there are new energy levels that are introduced that can be occupied by the electrons, and because of that, we will have essentially, yes, we can have intervalley transitions. Like, what does intervalley transition means? Because of the presence of strain, some of these energy levels now have a, some of these confined energy levels have a different spacing and a different characteristic, and the others have a different spacing and a different characteristic. So an electron can not only move among these energy levels, they can also jump from here to here. So we have intervalley transitions, and this was also true in the previous case. However, in the previous case, what happened is in the unstrained case, all of these six bands were having the same energy, so they were degenerate. So electrons could actually move relatively freely from one of these subbands to another without any restrictions. But now this energy difference that has been introduced here creates a kind of a barrier. Now electrons can move from this subband to this subband only if this additional energy is available from somewhere. In the event that it is not available, such intervalley scattering will not take place. Now, what effect does that have? The effect that it has is as follows. We should remember that this is an EK diagram. So, whenever I talk about K, I mean the momentum. So, this comes from our very beginning of our course. So, a lobe here, which has higher Kz values, implies that a larger momentum component is along the z direction. For here it is along the x direction, and for here it is along the y direction. So these are essentially electrons that are moving in different directions. So when there is an intervalley scattering, what essentially happens is the direction of my electron's motion keeps changing. So that is effectively what we think of when we think about scattering. So when I have an electron moving in a direction, if it is scattered from here, it will move in a different direction. Again, it will get scattered, it will move in a different direction. So the changing of momentum is exactly what we understand as scattering. So when electrons move from one subband to another, there is a change in the momentum, and because of that, we have scattering. Now, in this case, in the straight case, we now have two subbands and ladders that are forming. And because of that, the intervalley transition is no longer possible simply because an energy difference has been introduced. So, since that is the case, what will happen is the electrons will no longer be as likely as before to change their momentum, which implies the electrons will scatter less in such channels. Since there is low electron scattering, there is high electron mobility. Since there is high electron mobility, we have better conduction and therefore a better IV characteristics. So that is the fundamental aim for doing strain engineering in semiconductor devices. Now, these concepts, of course, the reason I am explaining all of this theory is if we can look at the assignment questions for week 12. Of course, I shall not be discussing the questions themselves. You'll notice that it is directly asked like what happens, why do we have increased mobility, and you'll see that there are again further questions regarding the notion of the effects of strain in a material. So the reason I explained all the concepts before is to ensure that you can answer these questions relatively easily if you watch the videos for this session. So now returning.
So, sir,
Yes.
if we need better mobility, we will
Yes.
need constant strain in that device.
Yeah, but constant, like you are not like, I mean, let me just move out of the slides for a second. Uh, and just clarify this. Let me stop presenting for a brief moment. So see, when we are talking about constant strain, it is not as if we are physically going and pushing it. As I mentioned before, the strain is embedded in the design of the device itself. So when I'm fabricating the device, the strain is introduced. So that strain is constant for as long as the device exists and functions.
Okay, sir.
Okay, so as I let me go back to the slides now. Um, yeah. So yes. So as I mentioned, yeah, we shall yes do that in a bit. As I mentioned here, like see, this is essentially how I'm depositing the gate on my semiconductor substrate. So after I'm depositing, that is not going to change. Even in this case, like this is how the device has been fabricated. So this strain is going to be there unless and until this material itself doesn't burn out or get eroded or suffer some kind of a chemical degradation or something like that. Unless those things don't happen, this strain is always going to be there. So
Yes,
your
sir.
question would be better answered over here. So there are multiple ways to implement the strain. So one direct way is to have like what do you call these things? Like what are these called? I keep forgetting this. So like these aren't compounds per se. Like we essentially have semiconductors containing multiple intrinsic materials. So we have silicon germanium and silicon. So silicon has this kind of a lattice constant, and silicon germanium, depending on the stoichiometric ratio, like the fraction of germanium present in this, will have a lattice constant that varies like this. So essentially, by increasing the amount of germanium in the material, a silicon germanium interface, if I can grow it in that fashion, will always have an intrinsic global strain because of the lattice constant mismatch. Now, this is the way in which globally strain can be imposed on a semiconductor. Another way is when we have a local strain definition. So, in this, what we essentially do, like that is essentially what I described before, we change the geometry of the gate. Like we essentially have an enveloping gate, or we have double gates, or some other kind of a configuration like silicon on insulator configuration where the strain is applied locally by the gate terminal. So essentially from point to point on the device, we implement these strained regions, and therefore in those strained regions we will have the enhanced electron mobility and other behaviors. So that brings us to the end of the discussion about strained silicon devices. Uh, in the last week's session, I had also like taken some extra time to talk about some of the recent research work that is being done. So you can go back and see those videos to you know see how these things are implemented and how these devices are functioning. At least insofar as simulations or things like that are concerned. So now we move on to the other part. Like there are three topics we shall be covering in today's discussions. The first topic was, of course, the conclusion of strain engineering. The second topic is thermoelectric effects. So this will be like a solid chunk of like there will be a good number of questions from thermoelectric effect in your assignments. There'll also be a few questions in your exam. Um, and the last part will be quantum dot devices. So yeah, now moving on to thermoelectric effects. Uh, in the case of like it will be easy to understand thermoelectric effects directly if we use the Landauer model of conduction. It is also possible to explain thermoelectric effects from the bulk semiconductor phenomena, but using the Landauer model will make the explanation significantly easier. So this is the current integral. This comes from the Landauer theory of transport. So again, for our discussions in this part, we shall consider the old two-terminal device. We shall not be looking at three-terminal devices. We are looking at a two-terminal device where we have a source, a drain, and a channel. So for this, we know that this is how we write the current that flows between regions. So this I call region 1, this I call region 2. So from 1 to 2, the current flow is given by this integral. Now, of course, the only non-zero components, the only thing that changes with, like if these two quantities were identical, then this entire term becomes zero and therefore the integral will vanish, which implies there is no current. We know that T of E, the transmission coefficient, and M of E cannot be zero. We've done the calculations for these things, so we know that these quantities are never zero. But if F1 minus F2 is zero, then of course there is going to be no current, and that is typically the case for a device in equilibrium. However, in general, for a device in operation, F1 minus F2 is never zero. One case that we have observed where F1 minus F2 is never zero is first when we apply a bias voltage. So this is what happens when we apply a bias voltage. When we apply a voltage, it is equivalent to shifting the Fermi level of the device. So the Fermi level is the point, like this is essentially where we have the Fermi level. Now applying a voltage will shift the Fermi level. So the Fermi level for, so if I have a voltage difference of delta V from the source to the drain, and let me assume that the source is grounded and the drain is given the finite voltage, then the drain Fermi level will be shifted and the source will be like present at the same level. So this kind of difference, which is given by the Fermi window function for small voltages, uh, gives us the electronic conduction. So this is the first way in which F1 minus F2 can be made non-zero. Another way, of course, like if we again remember that F is equal to 1 upon 1 plus exponential uh, E minus EF upon KBT. So how can we create a difference? We can also like we can shift the energy levels. So that is essentially what we do in the case of the uh, biasing voltage. Alternatively, we can also change the temperature. So if we change the temperature, again F1 minus F2 will be non-zero, and therefore there is going to be a charge conduction between material 1 and 2. So yeah, so for small voltages, F1 minus F2 can be written as minus dou F naught by dou E times delta Q delta B. So this is from the Taylor series expansion. And this quantity is the Fermi window function as mentioned right here. Similarly, we can also write the same for the temperature difference. So we can again do the Taylor series expansion in terms of the temperature. Like previously, when we did this Taylor series expansion, we assumed that the temperature was a constant. Now over here, we will assume that the energy is a constant. We will assume that no external voltage is applied. And then by doing the exact same analysis, we shall get for near equilibrium cases and small delta t's. So that is also like important to remember. We'll get that F1 minus F2 is approximately minus dou F naught by dou TL. TL is the lattice temperature. So yeah, that should also be remembered that when we say that apply different temperatures across two materials, we do not mean that we are changing the temperature of the surroundings on both sides. The temperature that we are talking about here is the temperature of the lattice. So in each and every one of these cases, whenever we have done written the Fermi statistics or even Maxwell-Boltzmann statistics, the temperature refers to the temperature of the lattice. Okay, give me just 1 second. Yeah, one more second. Yes. So that is the first part. Additionally, one more thing should be noticed. Can I draw that somewhere over here itself? Okay. rather than looking at the Fermi levels, let us for a second consider the. Let me change the thickness of this thing. Okay, this is at the lowest thickness. So let us consider the band diagram that we draw. So this is the band diagram for a n-doped material. Now for an n-type material, if we increase the temperature, of course the Fermi function is going to change, but additionally, another thing that we can infer is that more electrons will jump from the donor level onto the conduction band. So I have the conduction band, the valence band, and so essentially what will happen is increasing the temperature will imply more electrons can jump up to this level. So boosting the temperature will give me more electrons. That implies the current will be comprised, like the thermoelectric current will be comprised of electrons moving from. So if I have two different temperatures in two regions, there will be less electrons on one side, more electrons on the other side. Electrons will migrate from higher concentration to lower concentration. So the electrons will move from the region of high temperature to low temperature. However, if I have a p-type material, so the Fermi level is going to be, the acceptor level is going to be over here. So this is an n-type material and this is a p-type material. So in a p-type material, the Fermi level is going to be below here. Again, increasing the temperature would imply more electrons would jump from the valence band onto the acceptor level. And because of that, in the high temperature region, there will be a higher concentration of holes, and in the low temperature region, there will be a lower concentration of holes. So in this case, the holes will migrate from the high temperature region to the low temperature region. So as you can see, depending on the type of doping in the material, the charge carriers that move from the high temperature region to the low temperature region changes. So this is very important. The temperature difference causes a current flow, but the sign of the current depends on where the channel is located and what kind of a material the channel is made of. So previously, when we were looking at the current due to, so this is important. So previously, when we were talking about voltage biasing, we knew how the electrons were going to move. Like we knew that the electrons will essentially move from what to say, like a higher energy state to a lower energy state, and then the what to say, like since electrons have a negative charge, it will essentially move from the lower voltage terminal to the higher voltage terminal, and that is usually assumed to be the negative direction for the current flow. So the current is written with a minus sign. So that's what we see over here. Whereas here, the sign of the current depends on what kind of a doping the material has. So that is an important thing to remember here. So from that, the exact, like if we do the complete Taylor series expansion, this is what we will get. So how do we do this? We can look at the first order Taylor series expansion. So f of t plus delta t will be given by, which is equal to f naught, that is f at t, plus delta t times dou f naught upon dou t. Again, remember that T here is the lattice temperature. You know what? I think I'll rather call it T naught because I'm using a derivative here. So now, if we take the temperature derivative, we will see that since the Fermi function, again, as I wrote before, is of this form, exponential e minus ef upon qbt. Therefore, when we take the derivative of this, what we will have is like I will essentially have an E minus EF upon KBT term coming out before we take the derivative itself. So this factor will also be present. A 1 over T factor will also be present when we are writing the difference in the uh, Fermi functions. So another, additionally, what we should remember is that in a realistic scenario, we will have both a voltage difference and a temperature difference. So in this case, we can approximately write for a small voltage difference and a small temperature difference. So from this, essentially this quantity will be this. So in that case, we can write like del f of del t will essentially, so let me just do the direct temperature derivative here. So that will be minus 1 over this quantity, the whole square. I'm not going to write it again. And then we'll be taking the derivative of this. So that is going to be exponential of E minus EF upon KBT. And then we will differentiate what is on the inside. So that is going to be E minus EF upon KBT minus T squared. So it's going to be a product of these three terms. Now, if we were to take the derivative with respect to the energy, I will have this term, I will have this term, and I will have this term, but there will be no negative sign here, and there will be no 1 over T square. So the additional terms that are appearing are uh, the oh, sorry, when I'm doing that, dou f upon dou E, I will just get a 1 over kBT term coming out of here. The E minus EF term will also not show. So the additional factors that we have correspond when comparing to the energy derivative are E minus EF and TL. So that is why we are kind of writing the temperature derivative in terms of the energy derivative. Now, why are we doing this? Because we know that this energy derivative is the Fermi window function. We know the properties of this function. We have studied these things, and when we also know that doing the integrals with this function gives us the Fermi Dirac integrals, and we know the properties of those integrals also. So that is the reason why we are recasting this in this. Of course, this approximation is true only if delta t and delta v are very small. Essentially, delta V has to be very small compared to EF, and delta T has to be very small compared to the lattice temperature TL. So because of this, what we will have are now again in our low bias derivation for the Landauer, like the ballistic channel, we were able to derive the conductance of a ballistic channel. So that essentially was a function of E, and we integrated that, counting the number of modes and so on and so forth. So now, similarly, the integrals over here would yield a conductance, a specific conductance for energy, and a temperature dependent conductance. So this quantity will have the units of conductance, whereas this will not have the units of conductance. This will be ampere per Kelvin. This would be ampere per volt, which is the units of conductance, whereas this is essentially what our thermal coefficients are. Because ideally speaking, we should be able to write I, the thermal current IT is some S times delta T. Like this is what we want. This kind of a formula is what we want. And from here, from this expression, we can see that that will kind of be the case. And of course, this is the specific conductance that we have derived from the Landauer transport model. So with that, yeah, we come to the end of these slides. Let me move on to the next set of slides. Yeah. So, sorry, my last slide. Yes. Yeah, this is a recap of the strain phenomena. Yes. So now we are at the temperature phase. Yes. So this is the shifting of the Fermi level due to a bias, and this is the shifting of, like, this is the change of the profile. Yeah. Alternatively, we can also remember it this way: when we apply a voltage difference, there is, okay. So that's drawn in there. There is a shift, whereas here the profile itself changes as we increase the temperature. So when both of these effects are combined, there will be a shift and the profile will also change. And thanks to our approximation, now this combined effect can be treated using the same derivative, energy derivative of the function. Of course, this is an approximation for small voltages and small temperatures. Now, one can be motivated to ask, why are we doing this? Why are we not just considering a change in temperature and not a change in voltage? Because in a realistic scenario, what will happen is, like, as we know that when we have our two-terminal device, we have discussed by now that energy loss occurs only at the interface. So yeah, let me just draw the diagram more clearly so that the things can be explained. So we have this, and so, like, we essentially have energy losses occurring here and here. So whenever there is an energy loss, there will be a temperature change. That implies that even when we are not applying some kind of an external, like, temperature gradient, by virtue of current flow itself, the source and the drain, like, over a period of time, will obtain different lattice temperatures. So in reality, when we are considering the function of a semiconductor device, even the application of a simple voltage will create a temperature difference, as the device keeps functioning. Therefore, if we are looking at the realistic functioning of the device, this is essentially how we write the uh, differences in the Fermi level, and therefore this is kind of how we shall write the current that flows. So additionally, now, yes, so this is the, yeah, now what should be remembered is this: a material does not only conduct currents. Way back, in our high school syllabus and whatnot, we have also learned that energy can be transferred through heat conduction. So when a temperature difference exists, there is also a heat transfer from the material. Now, what is heat transfer? Heat transfer is essentially a transfer of the lattice vibrations from one region to another, because temperature is given by the vibrations of a lattice, like the vibrations of a given lattice. The more it vibrates, the higher the temperature. So the charge current is the flow of electrons, and the heat current is essentially a transference of these, lattice vibrations, which can be seen as even a phononic transfer if we are going down to the microscopic level. However, we shall not be doing that. So there are actually two currents here. So we have I, which is the charge current, and then a heat current, that is IQ. So now, what is the direction for IQ? IQ will always go from the high temperature region to low temperature region. So that comes from the, what law of thermodynamics is that? That is the zeroth law of thermodynamics, if I'm right. Yeah. So heat will always flow from a hotter body to a colder body. So the heat current will always go from the high temperature zone to the low temperature zone. Whereas the charge current, it depends on what kind of a material we are looking at. So the heat current is always going to have what to say, like a fixed direction with respect to the external temperature difference, whereas the charge current will depend on the kind of doping. So again, uh, if we look at the heat current expressions, we can also express that in terms of our Landauer integrals. So the heat current from region 1 and region 2 can be written in terms of their respective Fermi levels like this. Again, this is the specific current at a certain energy. This whole quantity needs to be integrated, similar to the charge current that we see here. So the heat current can also be written in terms of the voltage difference and the temperature difference in terms of these two coefficients. As you can see, ST is common to both of these. Again, the names of these coefficients I will tell you in like as and when we get there. So, so the heat current again can increase or decrease with respect to the temperature difference and the voltage difference by the same reasoning that I have described over here for the presence of what to say, like a temperature difference even when only an external voltage is applied. So yeah, wait, why are the slides repeating? That must have been an error. Yeah, I'll change that when I'm uploading these slides. So, yeah, again, we know that this is the expression for the differences in the Fermi level, and we also know that this is G of E. Therefore, it is possible to represent St of E in terms of G of E because the only thing that changes from here to here is this additional factor. So over here we have G of E is 2q square upon h. This is the quantum of conductance. T of E, M of E into the Fermi window. Whereas over here, what we will essentially have is a T of E, M of E, and a 2q upon h. So to make it equal to G of h, I will have to multiply and divide by a q. And of course, there will be a minus sign coming from the Fermi window function itself. And additionally, there is the E minus EF and the TL factor. So again, KB is not present here, so we multiply and divide by KB. So this is the relationship between the thermal uh, coefficient, which is referred to as the Sore coefficient. So ST is the Sore coefficient. That relates itself to the specific like conductance at a given energy level by this factor. Again, as you can see, the sign of the Sore coefficient will depend on the position of EF. So for a what to say, like n-type material, EF will be closer to the conduction band. For a p-type material, EF will be closer to the valence band. So it depends on what kind of a current we are computing this integral for. So this sign may be positive or negative depending on like if we are looking at whole current, we will be looking at valence band energies. Therefore, this will be of a negative sign. Now, if you are looking for whole currents in an n-type material, then this will be a larger difference. So that is the thing. The sign change with respect to the material doping comes from the change in EF, essentially. So that is the thing. So ultimately, we write the total current as G times delta V, which is simply known as the conductance. And this is the Sore coefficient, St times delta T. So this is the charge current as a function of in the presence of thermoelectric effects. Now the heat current can again be derived similarly. Now in this case, again the Sore coefficient shows up. However, we also have the K naught delta T, which comes from the Taylor series expansion with respect to the temperature. So this is how we shall write the Heat current, yes. So the heat current depends on the energy difference between these two materials. So this is the integral for the heat current and this is the heat current. Therefore, as you can notice, there is no electronic charge present here. There are no units of Q. Heat current is a literal transfer of energy. So we are actually so we are actually concerned with the energy difference in these materials. So this is the heat current, the heat transfer, the heat flux. So in this case, what we will have is, I think this is the Peltier coefficient, K naught. I'm sorry, I do not remember the name yet. I think one of the later slides will have the name for K naught. So again, following the same scheme of derivation, we will arrive at this particular expression. K naught, like we can find that K of E again connects to the conductance, the specific conductance by this expression E minus EF1 upon Q square TL. Of course, we are assuming that region 1 is of the higher temperature. If region 2 was of the higher temperature, then this would be replaced by E minus EF2 because the heat current always goes from the higher temperature region to the lower temperature region. Okay, so the coefficient here will only contain the information of the higher temperature region. Please remember that. So, yeah, I'll leave the. Why is it not? Yes. I want you to erase. Right? Yes. So now, what is the Seebeck voltage? Sorry, what is the Seebeck effect? The Seebeck effect is essentially what I described before. When an external voltage is applied to a material, there is going to be both a heat flux and a charge flux. And because of that, there is going to be a hot electrode and a cold electrode. And depending on the nature of the material, this temperature difference might either assist the electron, like the charge conduction, or resist the charge conduction. So now we are looking at the an N-type semiconductor. So over here we know that the electrons move from the high voltage terminal to the low voltage terminal, and because of that there is a hot terminal here and a cold terminal here, and we know that electrons again move from for an N-type material, electrons move from the hot region to the cool region because of the positioning of the Fermi level. Therefore, in this case, because of the Seebeck effect, the uh, current is augmented. If this were a P-type material, then the Seebeck voltage would be a back voltage. So, essentially, what do we mean by Seebeck voltage? There will be a back current, that is a charge current that is flowing because of the temperature difference if this were a P-type material. So, depending on the conductance, like if we ignore the thermoelectric effects and if we just treat this as a material with, sorry, if we treat this as a material with a conductance G, then when we apply some kind of an like voltage across this material, we would expect the current to have a certain value. However, because of thermoelectric effects, if this were a P-type material, that current would have been lesser. So that is equivalent to a reverse, applying a reverse voltage independently and kind of reducing the effect of this voltage. So the Seebeck effect can also be interpreted as an internal potential in the device. So for a N-type material, the Seebeck voltage is positive. For a P-type material, the Seebeck voltage is negative. Of course, how can we write the voltage difference? The voltage difference can be written in terms of the Kirchhoff's law essentially. So it is I times R minus S times T. So S times delta T. Now R is of course 1 over G. So from that, we can essentially get the Seebeck coefficient, which is St upon G. Like delta B can be written as I times I upon G minus St by G times delta D. So this is the voltage difference here. So the actual change, like this quantity corresponds to the Seebeck effect. So this is where I'm getting the Seebeck effect from. Of course, the quantity St will be positive or negative depending on the doping of the material. And like, so this quantity will tell us how much, like, so this is IR, or rather R times I, and this will be S times delta T. So this will tell us how much the Seebeck effect is, Seebeck voltage is being applied. So S times delta T is the Seebeck voltage, and the Seebeck coefficient is given by the Sorey coefficient divided by the conductance of the material. Again, all of this is for small voltages and small temperature differences. So yeah, that is the Seebeck effect. I think, yeah, this slide ends with the discussion of the Seebeck effect. Uh, yes, now we come to the last set of slides that we shall look at for today. Again, this is a review of what was done previously. Um, yes. So, yeah. So, Peltier effect is kind of the counterpart of this. Like, what we are looking at is we are assuming that a current is flowing through the material. So previously, the Seebeck effect was the thermoelectric effect that came from the application of a constant voltage. Now we are assuming that a constant current is flowing. So the current is fixed, and because of that, we will like to see what kind of a temperature change happens, and through that, we will see what kind of a heat current flows through the material. So yes, uh, so the yes, the quantity cannot essentially relates to the Peltier coefficient, the Peltier coefficient. So initially we assume that the temperature, the material has the same temperature. Now, in this case, we know that the electrons, like the current is flowing in this direction, that implies the electrons are moving in this direction. So since the electrons are moving in this direction, what we will essentially have is a heating effect that occurs over here. Now, why does this heating effect happen? That is essentially the Joule effect. So, when we have electrons moving from here to here to enter this channel, it is in this channel, and like, kind of it has to lose energy, like it has to dissipate energy into the channel, release energy into, not the channel, this electrode, essentially the drain, in order to move into the drain, in order to complete the current circulation. So since it is dissipating energy into this region, it is releasing energy into this region, this electrode will get heated up. Similarly, over here, for the electron to enter the channel, it has to gain some energy, which implies it is absorbing that energy from the lattice. So since it is drawing energy from that lattice, this electrode cools down. So now I have a cool electrode here and a hot electrode here. Again, remember, the Peltier effect depends strictly only on the direction of the current flow. Doesn't matter which charge carriers are flowing, because for any charge carrier that we are considering, even if we are looking at the holes, we will actually look at holes jumping in this way or that way. So when we are looking at the motion of charge carriers, the impact, the heating and cooling effect will be the same. So unlike the Seebeck effect, which depended on the material characteristics, the Peltier effect is essentially only dependent on the direction of the current. So this is kind of a generalization of the Joule heating effect. So yeah, the heat current is given by this expression, which the derivation of which we have followed before. So from this we can write, essentially we can combine these two quantities, and write it as pi times I, and this quantity is the Peltier coefficient. So there is a temperature difference that is formed that comes about as a result of the applied current. So TL times S, essentially the lattice temperature times the Sorey coefficient, gives us the Peltier coefficient. The Seebeck coefficient came from the Sorey coefficient divided upon the conductance of the material. So these are the, what to say, like general expressions for like diffusive transport for heat current and charge current. So again, substituting, we can get all these integrals. Insofar as I remember, I mean, these are here for your information and for your further knowledge. You most likely will not be tested on these topics, so I'm just leaving it as it is here. So, yeah, moving on. Now we come to the last section of today's discussion and the last topic to be covered in the course. So here we are talking about quantum dot devices. So quantum dot devices are, in many ways the like this is what the
Sir,
state of the art. Yes,
sir, when we refer to the term quantum computing, do we refer
yes.
to the quantum dot devices?
Oh, no, actually, no. So, in quantum computing, I mean, I thank you for asking this question because quantum computing is essentially my area of research. So, yeah, thank you for allowing me to speak something about my PhD topic. So, no, when we are talking about quantum computing, what we essentially do is we, like, just like if you remember in this case, when we are looking at conduction, previously, like in bulk transport, we did not assume the quantum nature of the electron to account for the transport properties. Whereas when we move down to land hour transport, and of course, as you are going to see here in the case of quantum dot materials, we will consider the quantum mechanical behavior of the electrons. So that is what we are, talking about when we are talking about quantum dot devices or nanoscale devices in general. In quantum computing, similarly, computing in general is processing of information. I take some kind of an input, perform some kind of an operation, give an output. That information can also be transferred in a quantum mechanical fashion. So quantum computing is computation done on information that comes from a quantum mechanical fashion. So essentially, like classical information is presented in terms of bits, whereas in quantum computing, we will see that the information is presented in terms of quantum bits, which are slightly different objects. And so quantum computing pertains itself with the construction of quantum bits, which can be constructed using quantum dots. So there are quantum dot based quantum bits. There are also other like superconducting quantum bits or even atomic ionic quantum bits and so on and so forth. I mean that we are not going to discuss in this course. It's like totally out of syllabus. But yeah, so when we are talking about quantum computing, we are using the quantum version of information. Over here, we are leveraging the quantum nature of the electron to move electron from point A to point B. In quantum computing, we will utilize the quantum nature of information to perform computational operations. So that is all. I hope that kind of answered your question.
Yes, sir.
Yeah. So now we come to the quantum dot or the 0D conductor. So what you see here in the screen are essentially the basic energy parameters. So now what is a quantum dot? A quantum dot is a device that has confinement in 3 dimensions. So we have, uh, I should write it properly because 3D confinement might actually sound weird. So we have, and I have to use this, we have 3-dimensional confinement. So you can ask, okay, so how do we confine an electron with 3 dimensions? So for that, I will briefly, like very briefly, talk about the stuff that was covered in the previous week. So when I have a MOS capacitor, when I have a when I have a MOS device that is kind of, yeah, when I have a silicon, I think I should put in more effort into drawing this. Yes. So I will have this, yes, and I have a layer of insulator, and then on top of that, I have a metal. So now, in this, what did we find? Like ultimately study when we were doing mass electrostatics. When we apply a voltage difference between the substrate and the gate, we create some kind of a depletion layer is formed depending on the sign of the voltage. So this is the metal oxide and semiconductor. Okay, somebody is wishing to join the session now. Of course, they are welcome. Uh, oops, where would be? Yes. So we know that when we apply some kind of a voltage, a VGS, essentially a VG, and let me say I'm grounding this, we know that after a certain threshold voltage and whatnot, we form an inversion layer. Like essentially there is an inversion layer which is electromagnetically layer which is electromagnetically confined electrons. So when we are talking about confinement, it doesn't mean we are making a small material. It is also possible to apply a potential and confine them into a certain region. I mean, that is the whole concept of potential wells. So these two electrodes have kind of confined the electron in this direction. So we have an inversion layer that forms if Vg greater than Vt, some threshold voltage. Like this much we have studied in our course. So if this is true for this direction, then maybe I can apply two more electrodes here and confine the electrons in that direction as well. Like that is also like totally conceivable and possible. So typically we will see that quantum dots are not just very small pieces of material because fabricating that is extremely difficult. So usually quantum dots are um, yeah. So yes, I'm sorry. Yeah, returning to slides, yes. So usually quantum dots are formed by having a bulk material, but we create different kinds of interfaces and we place multiple electrodes and apply the correct, sequences of voltages and biases to confine the electrons to a small region in that bulk material. So when we are talking about the formation of a quantum dot, we don't literally like create a dot. We create a region in a bulk material where the electron is trapped. And that trapping is usually done by creating a configuration of metallic electrodes through which different voltages are applied. So this part, like, I mean, for people who want to know how quantum dots are practically constructed and implemented, like, this is for their benefit. And that is how three-dimensional confinement is done. So when we say confinement, this is mostly electromagnetic confinement. Electromagnetic confinement. Of course, it is perfectly possible to deposit a very small amount of semiconductor onto a device and place two electrodes on that side. Such physical quantum dots have also been constructed. In fact, several years ago, like 6 or 7 years ago, people used atomic force microscopes, AFM probes to kind of pick very small, like 5 or 6 atoms of a material, place it, and have electron transference between them. So, in principle, constructing that is possible, but can those devices be manufactured on a large scale? Most likely not. Even the quantum dot devices that use electromagnetic confinement, maybe they cannot be manufactured on ICs because there are way too many electrodes and way too many controlling voltages. So when we talk about like packing multiple such devices, there might be crosstalk between voltages, and maintaining the confinement may be difficult. So those are also challenges when we are talking about quantum dot devices. But of course, the whole idea of engineering is to find out certain fabrication challenges or device design challenges, and eventually, in due course of time, find solutions to these challenges. So, I mean, that is where we all do our work. That is our field. That is our discipline. So that's kind of, oh wow. Okay, so it's actually possible to write outside of the slide. But yeah, I'd rather not take the risk. I'll just erase it and rewrite it properly. Oops. Yeah. So yeah, as I was saying, that is the whole idea of the design and implementation of quantum dot devices. So, for all practical purposes, most practical quantum dots are constructed using electromagnetic confinement and not mechanical confinement. So, okay, now the electrons are confined. What happens? What happens to an electron that is confined in all three dimensions? What essentially happens is the energy is completely discrete. So, completely discrete energies. Now, what does this mean? If you remember the notion of quasi 2D materials, we found that the electron is confined in kind of one direction, which leads to the formation of discrete energy levels. And in the other two directions where it is free, we kind of had, so essentially we had, for a quasi 2D material, again, from back in our course, we know that E was given by h square k parallel squared by 2m star plus some, n square pi squared h bar squared, yeah, h bar squared over here, by 2m star some lz squared. So this part was continuous and this part was discrete due to confinement. Now we are kind of generalizing this notion to all three dimensions. So if I'm confining a material in all three directions, this continuous energy term, like let us say I'm confining a material in two directions and leaving it in only one. So I will have two different terms for discrete energy levels and I will have one term for continuous energy level. Now if I confine it in the third direction also, I will have completely discrete energy levels. So that is, yeah, that is essentially what we are writing or drawing when we draw this kind of a configuration. So we have completely discrete energy levels, and of course, like when I draw this, these levels can also have some kind of a degeneracy. But for the sake of simplicity, we are not considering that. We are just assuming that these are all, discrete, non-degenerate electron energy levels. So at each level, we can pack in two electrons. If there was a degeneracy at each level, it will be multiplied by the level degeneracy of that. So this is how we stack the electrons in a quantum dot. Now, the definitions of these quantities are important because, again, this is what your assignment questions are kind of based on. So we have two ideas, which essentially comes from atomic physics. we have the notion of electron affinity and ionization potential. So what is ionization potential? Ionization or ionization energy, it is energy.
The energy
Yes,
for which the outermost electron can
yes,
be removed from the valence
yes,
band.
you're correct. Energy required to remove one electron. Now you can ask, like, why am I just saying it is one electron? Because if I supply some energy, like, it is extremely rare for a lower energy electron to absorb it and kind of jump up. Even if that happens, eventually what will happen is one of the higher energy electrons will jump down to the lower energy levels. So whatever we do, when I supply some energy, one of these electrons is going to jump out of the system. So we have now, as you know, that these discrete energy levels actually go all the way up to infinity. That does not mean that the electron is always trapped in a system, because for all practical purposes, if an electron gets a high enough energy, it can kind of sorry, it can kind of escape from the material. This is, similar to the concept of escape velocity or things that we have in gravity. Like, if we have a spaceship or a rocket which travels at some kind of velocity that is over a certain value, for earth I think it is around 11 kilometers per second, then it is no longer trapped by earth, it will just fly off, it will never come back. Like, earth's gravity will never be able to attract it back. So similarly, there is a certain amount of energy beyond which the electron is no longer confined in this quantum dot. Although it is possible to define quantum dot energy levels for, very high, like potentially infinite energies, in practicality, depending on the electrode contacts and the environment, after a certain finite energy, the electron can be said to no longer be confined in this material. Okay, so that level is referred to as the vacuum energy. So at vacuum energy, the electron is no longer confined. So the ionization potential is essentially the energy difference between the highest energy value to the vacuum energy. So the ionization potential, let me write that here. The ionization potential is equal to E. HOMO is the highest occupied molecular orbital or highest occupied energy level. So I'm going to use that term here, E HOMO minus E vacuum, or the other way around essentially. So it is the, magnitude of this. So this is, like, I'm saying negative because this energy has to be kind of supplied into the system. Okay, so the magnitude of the ionization potential is essentially this. It is the highest occupied energy level, the vacuum level, and the vacuum energy level is also referred to as E equal to 0. Because generally when we are talking about bound electrons, we give them a negative energy value. So when those electrons are kind of unbound, they reach zero energy. So the ionization potential is the what is it like highest energy of the electron available in the system. So that depends on how many electrons are here. Now, if this system had 6 electrons, then the HOMO will be here. The highest occupied molecular orbital will be here. Therefore, the ionization potential will be the difference between this level and the vacuum energy. Okay, so if you are given a configuration for a quantum dot, or some energy level configuration, you should be able to first find out what the highest occupied molecular level is like. This is important. Identifying this level is important. The next energy level is called LUMO, which is the lowest unoccupied molecular orbital. So the idea of electron affinity is the opposite of the ionization potential, in that now the system exists as it is. What is the lowest energy a newly introduced electron can have in this system? So for this case, the electron can only be introduced into the third level. Therefore, this vacuum energy minus E lumo. So electron affinity is, again, I'm not bothering with the sign, E lumo minus E vacuum. Now again, remember, in most conventions, E vacuum is actually said to be 0. I'm asking you to remember this because, I mean, if you have seen my previous week sessions, you know that whenever I'm asking you to remember something, it is probably related to an assignment question. So kindly keep that in mind. Um, so that is the point here. So this is the ionization potential and the electron affinity. So these are the two quantities. Now that will be important. It is also possible to kind of define the Fermi level between the HOMO and the LUMO, but the Fermi level no longer has the same meaning as before, because the Fermi level or the Fermi energy is a statistical quantity. Like, it comes from Fermi Dirac statistics, and statistics can only be applied to a very large collection of a certain particle. So statistics is something that occurs when we have a large number of particles present in the system. 4 is not a very large number, 4 is rather a small number. So for 4 electrons, although I can identify the midpoint between the HOMO and the LUMO, it is technically not the, I can call it, name it the Fermi level, but it is not going to play the role of the Fermi level or anything. Okay, so for the sake of formality, I can define the Fermi level, but in general, the quantities that are more important are the ionization potential and the electron affinity. Now, why is the electron affinity important? The electron affinity is important because when I want to introduce an electron into the system, I need to be able to supply or remove at least the energy corresponding to EA. And if I want to remove an electron from this system, I need to be able to supply an energy that corresponds to the ionization potential. And if I want to use this quantum dot device as quantum dot as a channel in my device, then I have to add and remove electrons from this system. So adding and removing electrons, like, that is essentially how the conduction will take place. So that conduction is defined strictly in terms of these two energy levels, ionization potential and the electron affinity. Now, similarly, for bulk materials, we had this notion of work function. So what is work function? Work function was essentially the difference between the Fermi level and the vacuum energy. That is the lowest amount of energy that I need to supply to the semiconductor to pull out one electron. So this is work function. Like, phi is for bulk semiconductor, and ionization potential is for the confined channel, completely confined channel. So the role of the work function is now replaced by the ionization potential. So typically, when we have a quantum dot device, it is constructed like so. We have two electrodes which are treated as bulk materials with respect to the quantum dot. Again, this does not mean I'm having a very small device and two bulk electrodes. Usually what happens is I have a single bulk material, and then on, okay, let me again try to draw this slightly properly. What we will usually have is a single bulk material where there are like a number of metallic electrodes, with different geometries coming in and out of it. So, like, there will be one electrode here, there may be like a couple more over here. Like, this is based on some design that I remember. In fact, some of these might even be joined. So there will be some weird configuration of electrodes. Because of that, somewhere over here, I can create a region of electronic confinement. So in this region, we will have electron confinement. So when we are looking at the device behavior, we will essentially look at electrons moving from this bulk region So these two are like, I mean, the whole thing is a bulk semiconductor. So it will move from the bulk region into the confined region, out into the bulk region again. So this part that I've drawn here can also correspond to this. So don't always think that a quantum dot is physically placed between two electrodes. In reality, most of the cases it is done, like this, because this is far more practical and easier to fabricate. So now how do we model? So this is again for bulk materials, this is how we do it. There is a vacuum level and there is a work function. And since there are many electrons here, the amount of like the electron affinity of this material is also equal to the work function. Because from the vacuum level, if it loses the same amount, it will come to the Fermi level. Therefore, the electron can be accepted. Whereas in this case, there is a finite difference between the ionization potential and the electron affinity. Remember this. Whereas in the case of the work function, it kind of replaces both the ionization potential and the electron affinity. Yes. So, yeah. So this is kind of the charge transfer model. Contacts are through metal electrodes because why? They have a large number of electrons, and they because of that, like they have a very large number of filled and unfilled states. So if an electron needs to jump into a metal, that is also possible. If an electron needs to jump out of a metal, that can also happen. So typically the contacts are metallic contacts for quantum dot devices, and the what is it like uh, equilibrium needs to be established initially. So, what is equilibrium? Essentially, what happens is electrons will be filled. So, let me go back to the previous slide itself. So, now I have the metallic energy level, and yeah, let me get in front. Yes. So, first we have the metallic energy level and its corresponding EF, and we may have discrete energy levels coming from here and here and here, and with different energy, and it will go kind of like this. So essentially what will happen is when there is a kind of equilibrium, and let me assume there is no external voltage that is being applied currently, so in that case what happens is, so I have the same thing here. Therefore let me just get rid of the EF. Yes. So yes. So this is kind of the Fermi level for a metal. So what will happen is, to make sure that there is equilibrium, all these energy levels will be populated by the electrons from the contacts. So there will be two electrons here, two electrons here, two electrons here. Of course, the number of electrons, remember, depends on the level degeneracy. For our simplistic model, we are assuming that these are just non-degenerate levels. Therefore, two electrons will come. And this level automatically becomes the HOMO, the highest occupied molecular orbit. And this level becomes the lowest unoccupied molecular orbit. The vacuum level can be somewhere above here. So the difference between that and that will give us the work function, whereas the ionization potential will be slightly higher because this energy level is slightly below the Fermi level. Okay, so now work function phi is equal to EF minus EV. So in equilibrium, this happens. So that is essentially what has been set up here. There is the Fermi level, there is the HOMO, and the LUMO. The ionization potential is usually larger than the metal work function because, of course, the energy level up until the Fermi level is filled. Uh, and what to say, like the LUMO, of course, depends on the the electron affinity depends on the LUMO energy level. That is the first energy level that occurs above the Fermi level. So this is kind of how we have an equilibrium that is established. Of course, now there is an important question. Here we assume that the source and the drain are of the same material. Now, what if these were not of the same material? What if they were, kind of above and below? In that case, how will equilibrium be achieved? Like essentially, instead of using a metal, let us say I'm using a highly doped semiconductor, which can also provide as many free electrons. So that equilibrium configuration cannot be obtained in a straightforward manner, because now we are talking about certain quantum mechanical transport of electrons. Remember, the electrons, when they move in and out of here, like in a completely discrete energy spectrum, in this case, like for energy levels of this kind, the electron can no longer be assumed to be a particle. Over here, it has to be treated as a quantum particle. So when I say an electron moves into the quantum dot and outside of the quantum dot, I should not look at it as a single particle jumping in and jumping out. Whereas it jumps in here, attains certain quantum properties, and because of that, the behavior in here is quantum mechanical. And when it leaves, again, it leaves as a quantum particle. Only after it has entered this material can I treat it semi-classically or even classically. But as long as the electron is present here, the treatment must be quantum mechanical. Because of that, this particular solving this particular problem is not going to be easy. Typically, we use self-consistent methods to solve for these equilibrium and the subsequent current conduction issue also. So we use self-consistent methods, and in order to study the energy level configuration and all of these things, we use techniques such as density functional theory. Again, these things are beyond the scope of this course, but of course we can always mention what these are. So there is density functional theory, which is a theory that extends the application of quantum mechanics, especially the Schrodinger equation, to these bulk material situations. So density functional theory sometimes is also referred to as DFT. I think the very last lecture of this course will have a brief introduction to density functional theory. But again, for as far as the assignments and the questions are concerned, density functional theory is like well beyond the scope of the course. So you can, I mean, you need not pay too much attention to it. So yeah, that is essentially what happens. So now, again, for our two terminal device, we had a source, a drain, and a channel. So after studying all the modes and energy configuration, density of states, and all of this, the first thing we tried to do was kind of define the idea of conductance. Like how will electrons flow from point A to point B? How will they go? Like what will they depend on? These were the things that we studied. Analogously, for a two-terminal quantum device, um, what we will have is an equivalent phenomenon, but in this case we should remember, again, as I mentioned before, the electrons are no longer flowing from point A to point B, they are moving into a confined location and then moving out of it. So this process is actually better visualized as a charging and a discharging effect. So essentially, when, like, depending on the position of the Fermi levels and the initial content. Oh yes, please. I am sorry. I should have made a clarification. Previously, like, if it is also possible that this quantum dot, by virtue of its construction, can already have some electrons in it. So in case these electrons had some, like there were some electrons beyond the Fermi level, what will essentially happen is those excess electrons will jump into the drain. Okay, if there were no electrons present up to the Fermi level, then the source will donate. If not, the drain will accept. Okay, so depending on how many electrons that the quantum dot originally had, to achieve equilibrium, electrons would have moved from the source to the quantum dot or from the quantum dot to the drain. Okay, therefore, initially when the equilibrium is achieved, there is a kind of a charge transfer. Either the charge in the quantum dot increases or decreases. So this process, the charge transfer process, is referred to as charging. So when equilibrium occurs, the quantum dot is charged. And of course, because of that, the Fermi levels are, kind of shifted here and there because there is some charge transfer happening. And all of these effects can be represented by capacitors. So this is the most important part. Previously, when we were studying the 1D, 2D or 3D channels, we modeled that as a resistor. Landauer theory allowed us to define the conductance of the channel depending on the modes and the length of the channel and so on and so forth. Whereas in quantum dot devices, the Landauer theory, of course, cannot be extended because it's a 0D channel, and the charge transfer characteristics actually come from capacitances. So, how do we estimate that? Essentially, we use the same theory as before. So there is a vacuum energy level, and again, even for this discrete 0D state, we can define a density of states. Now, if you remember, for a 3D confined material, the density of states will usually be a sum of delta functions. E minus EI, sum over I. Like, if you remember, for 1D material, density of states is inversely proportional to the square root of energy. For a 2D material, it is independent of energy. For a 3D material, it is proportional to the square root of energy. But if we look at a quantum dot device, the density of states will usually be written as a sum of delta functions. So when we write that over here, we will be essentially substituting this over here. Okay. So again, now we will see how many electrons are moving. So we will find out what delta n is. Now, depending on that, we will know how much energy was transferred in or out of the system. So that will give us a delta E. And now that delta E divided by Q will give us a delta V. Therefore, uh, what to say, like that potential difference divided by the total amount of charge transferred will give us the capacitance. So the number of charges that are transferred are given by this particular integral. And so again, depending on the relation between E and EF, this quantity can either be positive or be negative. And from that, we kind of get the net energy that is transferred. And from that, we kind of model the quantum of capacitance, which is given by q square times g at the Fermi level. So now this is a constant number. So we multiply that by q square to get the quantum capacitance of the like essentially this is the charging capacitance of the quantum dot, and therefore we can write the energy change during charging or discharging is given by q square upon cq times delta n. So this is the expression for energy change during charging. Similarly, we can also study the effects of uh, like charge transference. Of course, for doing that, we need to use self-consistent methods. Um, since those concepts do not appear in the assignments and they also have very little bearing in the exams, I'm not discussing it. I don't mean that these topics are not important. Please pay attention to them in the lectures, and of course, like in a at a future date, if you want to revise these concepts, you can always come back and look at these lectures. You should, I mean, by now have the YouTube links for all the lectures in the course. So when that time comes, please come back and read those topics. But insofar as our discussions for solving, like this is a discussion session that is primarily focused on solving assignment questions. So because of that, I'm stopping today's discussion at this point. So this will be the last concept that we are looking at. So we have come to the end of this week's session. So, if any of the attendees, yeah, let me stop, not rather, let me just minimize this for a second. Yeah, if any of the attendees have any questions, you are free to like ask. Uh,
Sir, do these quantum dot devices are practically applicable?
yes, yes, yes. Like not in integrated circuits, but there are very many quantum dot transistors. There are quantum dot, as I mentioned, it is possible to construct quantum bits for quantum computing using quantum dots. There are actually many practical quantum bits that have been constructed. There are quantum dot sensors. There are quantum dot there are several devices that have been constructed using quantum dots. So quantum dots are used. They have been used for a very long time. The limitations that I suggested were for the design of quantum dot based transistors. Because when we are constructing practical devices, ICs and microprocessors, we need billions of such devices. Now, integrating billions of quantum dots onto a substrate or a die is kind of a challenge. Of course, I'm not saying it can never be surmounted. It hasn't been surmounted yet. And even beyond quantum dots, there are now devices called, like single electron transistors or things like that, where we are even like, when we are talking about quantum dots, we are allowing for the fact that a few electrons can exist in that region. Like by a few, it can also be like 50 or 60 electrons or even more, depending on the dimensions of the quantum dot. However, there are single electron transistors where the entire conduction and all the charge transfer process happens only through one electron. So in that case, like that is essentially the case where the drain source channel all are treated as nanoscale devices. So not only do we have quantum dot size devices, we have also moved beyond that. But again, the challenge here is how well can these devices be operated in a realistic scenario, like how resistant to temperature fluctuations and electromagnetic noise are they, like what kind of isolation that I will have to have, and in the long term, can I add these, like integrate several of these devices onto a single physical substrate and kind of build complex devices out of it. So that is the ultimate challenge when it comes to semiconductor devices. So I hope that answers your question.
Yes, sir.
Yeah. So I suppose, yeah, if there were any other questions, people would have asked by now. So yeah, just for the sake of completeness, to give you an idea of what goes where. Uh, yeah. So you can see these are the questions. So like you've been asked to calculate the electron affinity, you've been given the electron configuration, you've been asked questions about Peltier and Joule effects and Seebeck effects. They have been explained in today's discussion, so kindly use that. Ionization potential, electrostatic capacitance, quantum capacitance. Again, these things have been discussed, so you should be able to answer these questions. IV characteristics of quantum dot devices are also present. I've explained that as well. Some units and dimensions questions, like you can of course look these up. Uh, and there is also one about lattice constants. This should be a pretty straightforward question. I'm not going to go into any more details. And this is based on strain engineering. So essentially, everything that you need to solve the assignment questions for week 12 have been discussed in this session. Of course, these alone will not suffice. You will have to listen to the lectures first, and then you can come back and revise this. These should help you solve the assignment questions. So with that, we come to the end of this week's session.
Sir,
Yeah,
the pattern of the paper will be same as that of assignments.
yeah, it's an online objective questions.
Okay, sir.
So it's an online computer-based questions where you'll have MCQs. It will be the same as the assignments. We are not going to deviate from that. So yeah, that is the thing.
Sir, what all
Uh,
courses can we choose after completing this course?
okay, so that is kind of a hard question to answer because this is a relatively new NPTEL course and we are kind of independent from. So even as a research, like I can attempt to answer this question because as I mentioned, I am the PhD student of the course instructor, Professor Vishwendra Punia.
Yes, sir.
So we are kind of a disjointed research group. Like we are new. Like this course, this is only the second time it is running. So right now, I don't know. I don't think there are any other nanoscale device courses that are running on NPTEL on this. you can maybe pick up some kind of a device design course, that focuses on simulations and, there are, yes, you can, if people are extremely interested in learning about quantum dot devices and things like that, you can pick up some advanced solid state device courses that might be offered even by some physics departments where they deal with density functional theory and things like that. So if you want to learn, it essentially depends on what you're interested in. If you want to like move further along the lines of nanoscale devices, with 1D and 2D channels, then you can actually pick up some kind of a device design or a device simulation course where you can apply the concepts that you have learned here to simulate the devices using the methods that is taught in those courses. So this is kind of a, like, a multi-focused, like, this is not focused, this course, as you have seen, is not focused on one particular area. Initially we discussed a lot of physics, and then there was a lot of, what to say, like, we focused a large amount of time on land hour transport theory itself, like nearly half of the course was focused on that. And then we moved on to MOSFET devices and, electrostatics. So over there we came across a few techniques. So depending on which part of the course interests you, you can find a course that teaches that aspect and move forward with that. So
Yes, sir.
yeah, and as time progresses, like as more and more students come, and there is kind of a trend is established, maybe this course will find its place in the order of, NPTEL courses that are already present. Okay,
Sir,
so
as
yeah,
my branch is mechatronics,
uh-huh.
so how I can relate to this course and means.
Okay, mechatronics. So for your discipline, there aren't many direct connections because mechatronics is primarily an application-based domain. However, as I mentioned before, quantum dot devices and things like that are used in sensors and stuff like that. Like, especially the last parts that you have learned might give you some knowledge. Like, it cannot be something. I mean, I'm not saying it cannot be. To the best of my knowledge and, my understanding of things, uh, knowledge of semiconductor devices does not directly translate into expertise in mechatronics. But whatever you have learned here in the future, like, nowadays, quantum dot sensors are not used like extensively, but going forward, like in the years to come, these devices will become more and more prevalent. So in those cases, the things that you have learned in this course will help you identify the kind of devices you need to use for, your various applications. So from that standpoint, whatever you have learned in this course will benefit you most. This course is primarily aimed at people who are into device design and, device research. Essentially, this is a semiconductor devices course at its heart, and we are just kind of a gateway for, moving into, like, moving away from conventional silicon device paradigms to more advanced paradigms like silicon on insulator or quantum dot devices. But yeah, the notion is like they are the core audience, but of course other people who attend will always benefit from the knowledge you gain, because these devices, as time progresses, will become more and more common, and whatever you learn here will give you an advantage at that point in time, which will not be very far in the future. Like, I mean, 5 6 years ago when I was studying quantum computing, people said it's, not practical, it will never happen, and, it's all only theory. And now there are functioning quantum computers with, very large number of qubits, and algorithms can be
Yes,
implemented
sir.
and run. So things will change very fast. So this course will allow you to, like, kind of stay ahead of the curve, give you some introduction to the basics. And that is the thing, if you've paid attention to this course, you will not only know the names of these devices, you will also know something about their inner workings also. And that knowledge, at least in my opinion, and I think I can also speak to the members of my group, that knowledge is very important, to know how things work rather than just knowing what work they do. Okay, so
Yes, sir.
yeah, so that is that, so far as this week's session goes. Whether or not there will be a session next week, the NPTEL uh, like the folks over at NPTEL will decide. So if there is a session, you will see an announcement on the course page. If there is a session, that session will be exclusively focused on problem solving, and you guys can bring as many questions as you want. Like any assignment question whose solution that was not clear to you, you can post to me then, or even in advance you can post those questions on the forums, and I will directly fish out some of those questions and kind of address them during the session if the session happens. If it doesn't happen, if you have any questions, please post them on the forums. I will go through your questions and answer them there. Okay.
Yes,
All
sir.
right. So
Thank you, sir.
yeah, yes. Thank you all for attending, and thank you especially for the people who have stayed until the end of the session. So we will meet next week if there is a session. If not, it has been what to say, like a pleasure interacting with you guys over the last couple of months, rather 3 months, and I wish you all the best with your future endeavors, and I also wish you luck for the upcoming examinations, both the NPTEL and any other exams that you guys might have. So all the
Thank you, sir.
best, and thank you. I'm ending the session.